Hello and welcome to Ground Shakers, where we dig into the fascinating and sometimes frightening world beneath our feet. Today, we're talking about something straight out of a disaster movie: soil liquefaction. Imagine the solid ground you stand on suddenly behaving like a liquid during an earthquake. Sounds terrifying, right? This isn't fiction. It's a real phenomenon with devastating consequences, and understanding it is crucial for building safer communities. So how does solid earth turn into a soupy mess? The culprit is usually an earthquake. When the ground shakes, saturated, loose sandy soil particles try to settle closer together. But the water trapped between these particles gets squeezed. If this water can't escape quickly, its pressure builds up, pushing the soil particles apart. This is called increased pore water pressure. Essentially, the water pressure counteracts the forces holding the soil together, causing it to lose its strength and stiffness. Suddenly, that firm ground can't support anything. Besides earthquakes and waterlogged soil, the type of soil matters immensely. Loose, sandy soils are prime candidates. And of course, the stronger and longer the shaking, the higher the risk. Interestingly, scientists used to think liquefaction only happened in watertight conditions right near an earthquake's epicenter. But new research shows it can occur even with some drainage, further away, and with less intense shaking. The Earth still holds surprises for us. When liquefaction strikes, the effects are dramatic and destructive. Buildings can tilt, sink unevenly, or even collapse entirely as their foundations lose support. Roads buckle, bridges fail, and underground pipes for water and gas can rupture. You might see sand boils, eruptions of sand and water bubbling up to the surface, like mini volcanoes. Gentle slopes can start to slide sideways in what's called lateral spreading. In severe cases, large areas can become uninhabitable, leading to massive economic losses and profound disruption to people's lives. It's a stark reminder of the power of nature. But it's not all doom and gloom. Engineers and scientists are constantly working on ways to deal with liquefaction. First, they assess the risk. This involves investigating the soil type, groundwater levels, and the site's seismic history. Think of it as a doctor diagnosing a patient. Once the risk is known, there are several ground improvement techniques. We can densify the soil, literally shaking it down or compacting it with heavy weights or vibrations to make it stronger. Another approach is soil reinforcement, like installing stone columns that act like strong pillars within the weak soil, also helping water drain away. We can also improve drainage directly with gravel drains to relieve that dangerous water pressure during a quake. Grouting is another cool method, injecting substances like polyurethane or colloidal silica that bind soil particles together, basically gluing the ground. And there are some really innovative, eco-friendly ideas emerging. Think about using microorganisms to naturally cement soil particles, a process called MICP. Or even using recycled materials like construction waste or rubber chips. Beyond treating the ground itself, structures can be designed with liquefaction in mind, using deep foundations that reach stable soil layers below the liquefiable zone. So, soil liquefaction is a serious hazard, turning solid ground into a fluid threat during earthquakes. But the good news is that our understanding is constantly growing. Researchers are developing smarter ways to assess risks, and more effective, sustainable, and even environmentally friendly solutions to protect our buildings, our infrastructure, and ultimately, our communities. It's a continuous effort to build a more resilient world on ground that, sometimes, can be less stable than we think. Thanks for tuning in to Ground Shakers. Join us next time as we unearth another fascinating topic.